Hey everybody, we're going to talk about addition and subtraction formulas, another set of identities on your list. And oftentimes kids want to make the mistake that they can just put an operation over top of addition or subtraction. A common theme right here is, for example, kids want to take that squared and be able to distribute it in and say that that would be u squared plus v squared, which is actually incorrect. You have to actually FOIL together those. Because you cannot just distribute over top of addition in all operations. The same is true for sine and cosine and tangent. You are not able to distribute a sine over top of a u and a v if they're added together. So this video is going to talk about what you do if you need to deal with a situation where you have the sine of two angles added or subtracted. So we're going to go through a proof here. We're going to start with the cosine difference proof. And so I'm going to color code some things here and show you how we're going to make this work. So the purple angle is angle beta, and it's going to create the purple ray. And if I were to create a right triangle off of that by dropping down the leg and looking at the x and the y, the cosine of beta is going to be creating the x piece of your coordinate, and the sine of beta would be creating the y piece to that coordinate. If we were now to look at the angle alpha, which is going to be in blue, alpha is in standard position, and it's leading to a ray that's sitting in quadrant 2, and we're going to color code that blue also. Then if I were to drop a leg down to the x-axis for that angle, then my x value would be found by using the cosine of alpha, and my y value would be the sine of alpha. What I'm going to do now is take my 2 points and connect them with a segment. We're going to call that D. And then what we're going to do with this triangle is rotate it down to the x-axis. So the purple ray is now sitting on the eastern side of the x-axis, and the blue ray will be now in quadrant 1. And then the segment between them will still be D. And the angle that is formed now in standard position, we're going to call that alpha minus beta. And we're going to label that in green. And the alpha minus beta is coming from the green angle in the other triangle, where you're taking the entire angle alpha and subtracting from it the angle beta to get that angle that's creating that standard position angle on the unit circle on the right-hand side. So what we're going to do now is we're going to use the Pythagorean theorem and the idea of using a right triangle to find the expression for the distance d. So I'm going to draw a right triangle that connects the 2 points where the hypotenuse is D. And my vertical leg is going to be the sine of alpha minus the sine of beta, because the sine of alpha is the point from the blue point down to the axis, and the sine of beta is the purple point. So that little sliver of the leg would be sine of alpha minus sine of beta. We'll do the same process for the horizontal leg, where it will be the cosine of beta minus the cosine of alpha, because the cosine of beta would be the x value on the positive side of the x-axis, and the cosine of alpha would be the negative x value on the left side of the x-axis. And so when I take my right-hand side minus my negative left-hand side, I would get a leg that is longer by taking cosine of beta minus cosine of alpha. So now that I have that situation, I can come up with an expression for the length d of that right triangle by using the Pythagorean theorem. So we have d squared is equal to sine of alpha minus sine of beta squared plus cosine of beta minus cosine of alpha squared. I'm going to do the same process with the triangle on the right, where I'm going to drop my leg down from that point and create a right triangle, where I'm going to use that right triangle and the Pythagorean theorem to help us find the length of D. The horizontal leg would be 1 minus the cosine of alpha minus beta, because that ray is 1 unit because it's the unit circle, and we are subtracting away from it the x value of that point. And so that's how we get that horizontal leg. The vertical leg would be taking the sine value of alpha minus beta and subtracting from it 0. And so we have just the sine of alpha minus beta. We can get rid of that minus 0 because it's not necessary. So if we were to come up with an expression for the length of d using the Pythagorean theorem, we would say that d squared is equal to the quantity 1 minus cosine of alpha minus beta squared plus sine squared of alpha minus beta. In the next step, since our d squareds are equivalent, we can actually take our two expressions and set them equal to each other. So now what we're going to do is take some time to expand out this relationship that we've created. And so I'm going to take what I have highlighted in purple and we're going to foil that. We're also going to foil the blue highlighted section. And then lastly, we're going to foil the yellow highlighted section and create an identity that is going to be completely expanded out. Now that we have this expanded, we can start using some algebra and trigonometric identities to reduce things. So we have here is sine squared of alpha, and we have a cosine squared of alpha, which together create 1. We also have a sine squared of beta plus a cosine squared of beta, which creates a 1. And on the other side of our equation, of our identity rather, we have a cosine squared of alpha minus beta plus a sine squared of alpha minus beta, which creates a 1. Everything else is going to fall into line, and we're just going to pull that down and see if we can reduce this further. Now we can take the two ones that are on the right side and the two ones that are on the left side, and they would cancel each other out. And now everything, you'll notice, has a -2 as a factor, so we can actually reduce that away from everyone. And so what we have left is the identity. If you look on your trigonometric cheat sheet, you will have in the addition subtraction formulas section the cosine of alpha minus beta, and that's equal to the cosine of alpha times cosine of beta plus the sine of alpha times the sine of beta. You'll notice that after I rewrite it, I just rearrange some of my terms so that they match the same setup that's on your trig cheat sheet. So now we have that addition, subtraction, the subtraction formula for cosine proven. And off of that, we're going to be able to prove the other three. And so what we're going to do now is go to the sum of cosines and prove that. So we're going to take what we just got finished proving, and everywhere we see a beta, we're going to replace it with a negative beta, and we're going to then use our even and odd identities to simplify that. So in cleaning this up, the cosine of alpha minus negative beta would clean up to be the cosine of alpha plus beta, which is what we're wanting to see happen. On the other side, the cosine of negative beta, because cosine is an even function, that negative does not impact the overall signage of the term. So the cosine of alpha cosine of negative beta is equivalent to the cosine of alpha times the cosine of beta. The other term, when we have the sine of negative beta, because sine is odd, that negative actually does change the overall signage of that term. So what we like to do is we like to take that negative and shove it all the way to the front of that term and change the sign of that. So that term would be negative sine of alpha sine of beta. So using the difference of cosines, we've actually proven the sum of cosines using the even and odd identities. You'll notice that the cosine of alpha plus or minus beta, the plus or the minus matches, or I'm sorry, is the opposite of the sign between the two terms on the right-hand side of the identity. Now we're going to use the identity we just proved, and we're going to prove the difference of signs now. And we're going to take every alpha that we see and replace it with pi over 2 minus alpha. And eventually we will use the cofunction identities to simplify it. In simplifying the cosine of pi over 2 minus alpha plus beta, the parentheses is not necessary anymore there. So we actually can get rid of those parentheses because it's addition that's separating them. And what we're going to do is we are actually between the alpha and the beta, we're going to GCF out a negative. And I'm going to tell you why here in a moment. But when we do that, we would end up having the cosine of pi over 2 minus the quantity alpha minus beta once we GCF out the negative from the alpha as well as the positive beta. Using the cofunction identities, we can look and see that the cosine of pi over 2 minus alpha is equivalent to the sine of alpha. So we have sine of alpha times cosine of beta in the first term, and then we're going to do the same thing with the sine of pi over 2 minus alpha, and using the cofunctions, that is equivalent to the cosine of alpha. So the second term would be minus cosine alpha sine beta. If we revisit the first left-hand side, we have the cosine now of pi over 2 minus that angle, which is alpha minus beta. So again, using the cofunction identities, we can say that that's equivalent to the sine of alpha minus beta, which is what we want. So the sine of alpha minus beta is equal to the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. One difference that you'll see in the sum of signs proof and difference of signs proof is that the signage between them match. So the sine of alpha minus beta, you'll notice on the left hand or on the right hand side is separated also with a negative sign. We're now going to use our result, and we're going to do the same process by replacing all of our betas with negative betas in what we just came up with and simplify it using the even and odd identities. So the sine of alpha minus negative beta is equivalent to the sine of alpha plus beta, which is what we want. Using the even and odd identities, the cosine of negative beta, because cosine is even, that negative will not impact the overall sign of the term. So the sine of alpha times the cosine of negative beta is equal to the sine of alpha times the cosine of beta. In the second term, because sine is odd, again, that negative does impact the overall sign of the term and reverses it. So our answer there for that second term, we're going to shove it to the front, would be positive cosine of alpha sine of beta. So our sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the sine of alpha, plus the cosine of alpha times the sine of beta. My signs were incorrect. I just fixed them. In these next few examples, we're going to talk about how we can use these identities to help us find exact values of angles that we might not know specifically what their ratios are. So if I asked you to find the sine of 15 degrees, the problem is we don't know a 15, 75, 90 triangle as easily as we do the 45, 45, 90 or the 30, 60, 90. So what we do is we take 15 and we create it by a difference of two angles that we do know something about, 45 and 30. So the sine of 15 degrees is equal to the sine of the quantity 45 minus 30. Remember, kids often want to just distribute that sine in to both of those angles, but that is not allowed. So what we have to do is use our subtraction formula for the sine function and expand it. So we're going to go back to our identities and we're going to expand the sine of 45 minus 30 using our identity paper. So that would be equal to the sine of 45 times the cosine of 30 minus the cosine of 45 times the sine of 30. Now that we have that expanded, we can find those values because we know them. So now the sine of 45 degrees is equal to the square root of 2 over 2. The cosine of 30 degrees is equal to the square root of 3 over 2 minus the cosine of 45 is the square root of 2 over 2 times the sine of 30, which is 1/2. Our next step is to put these together and simplify. So the square root of 2 over 2 times the square root of 3 over 2 comes together as the square root of 6 over 4. Minus, and the square root of 2 over 2 times 1/2 is the square root of 2 over 4. And lastly, we can put that together and say that's the square root of 6 minus the square root of 2 all over the common denominator of 4. And that is the exact value for the sine of 15 degrees. We're going to use the same process to find the tangent of 7 pi over 12. We did not take the time to prove the addition subtraction formula for tangent, but it is on your paper. I let you take 7 pi over 12 and convert it into degrees because I think it's often easier for us to take a degrees and find two angles that add or subtract to it a little easier than it is with radians. So pi over 12 is 15 degrees. And just to do some quick math, 15 times 7 is 105 degrees. So 7 pi over 12 is equal to 105 degrees. So now what I'm going to do, because I don't know a lot about a 105-degree angle, I want to find angles on our unit circle that I do know information about that add or subtract to make 105. I'm going to use 60 and 45 degrees. I could have also used something like 135 minus 30 degrees and done the same process. I'm now going to take the addition formula for tangent and expand the tangent of 60 degrees plus 45 degrees. Now that I have it expanded, I'm going to take that expression and find the exact values because I can do that because I know all of those tangent values. The tangent of 60 degrees is the square root of 3 plus, and the tangent of 45 degrees is 1. I'm going to divide that by 1 minus the square root of 3 times 1. The next thing we want to do is rationalize the denominator so that we don't have that square root of 3 on the bottom. So what I'm going to do is multiply both the top and the bottom by the conjugate of the denominator, which would be 1 plus the square root of 3. I went ahead and just erased that one because it wasn't necessary to have there. So now what I'm going to do is FOIL everything on my top and FOIL everything on my bottom and clean that up. When you FOIL together conjugates, the middles will always drop out. So in cleaning that up, I'm going to combine my like terms in the numerator. So I'd be left with 4 plus 2 radical 3's, and in my denominator, that would be negative 2. I can simplify that one more step by taking a negative 2 out of everything, and so my final answer would be negative 2 minus radical 3. That's the exact value for the tangent of 7 pi over 12. Our last example wants us to solve the equation that's listed, and when I look at that, I see that I have two sign expressions that use addition or subtraction formulas. So what I'm going to do is use my addition and subtraction formulas to expand it, because remember, I'm not allowed to distribute that sign over top of addition. Now that I have that expanded, I can find the cosine of all my pi over 4's and the sine of my pi over 4's, because I know that those are radical 2 over 2. I'll do the same thing for the rest of the terms as well. Looking at what I have left, I have a radical 2 over 2 times the cosine, and I have a negative radical 2 over 2 times the cosine. Those two will cancel each other out. Putting together the sine terms, that would be the radical 2 times the sine of x when I put those two together. That would then be equal to negative 1. When I get x by itself, I would be left with inverse sine of the negative 1 over radical 2. When I try to solve that for x, I know that's got to come out of quadrant 4. So I draw a triangle in quadrant 4, and I label my opposite and my hypotenuse. Knowing that this is a 1, 1 radical 2 triangle, I know that the answer has to be a pi over 4. But I don't want to use negative pi over 4 because that's not in the domain, or it's not in the interval that they asked me to keep my answer in. So I actually want to communicate my answer as 7 pi over 4, which is one positive trip around the unit circle. I also know that sine is negative in quadrant 3, and so that would also develop a solution. So I'm going to draw a triangle in quadrant 3 and label my sides. Again, that creates a 1, 1 radical 2 triangle, but my answer would have to be communicated as 5 pi over 4 because we are in quadrant 3. So my two solutions to our equation that sit in the interval that they want it in is 7 pi over 4 and 5 pi over 4. That completes our notes over addition and subtraction formulas. If you have questions, please don't hesitate to ask, and I will see you later.